All right, I'll just close the door and then I'll kick this off. Wow, quite a gender balance. I'm still glad that you're all here. All right, welcome everyone to the fourth talk in our speaker series, Inside Data Journalism. Today, we're trying out something new, and that is to live stream our speaker. We have roughly, Lenny, whether you can see it, I can activate the video here to see. Yes, we have a couple of people in the room and even more joining online. So I'm delighted to welcome Lenny Bronner. Lenny is a data scientist whose work sits at the intersection of data science and, well, work in the newsroom. Lenny is originally from Vienna and is trained at Stanford. So Lenny, you have a bachelor's in mathematical computational science and a master's in statistics. Previously, Lenny worked at the media company Sidewire in California, but much of his career has been at the Washington Post on the newsroom engineering team. And there he built and led the live election forecasting models that a lot of readers relied on. It's I think one of the biggest election forecasting efforts out there in one of the biggest democracies out there. His coverage included the 2020 and 24 U.S. general elections, so high-stake elections. Lenny brings, and I'm sure he'll tell us more about that, a serious methodological toolkit to data journalism, and in doing so helps moving data journalism from visualization to rigorous inference, and that under time pressure, which we're not usually that used as academics. So with that, Lenny, I'm glad to have you with us. I'll hand over the floor to you. I'm admitting even more people joining. We will take questions at the end. If you have anything urgent to ask, just raise your hand. I'll try to keep an eye on both the chat and with that, over to you, Lenny.
Thank you so much for the introduction. So I think I can basically skip over most of this, but just sort of a quick reminder, I suppose. I'm a data scientist at the Washington Post. For most of my time, I was on the newsroom engineering team, but I'm now back on the data and AI team. For most of the time, I've been doing election modeling. I developed what we're at the Post call Post Pulse, which is sort of the umbrella branding for all our election models. My background's in applied math and statistics, and like someone said, I'm originally from Vienna. Election modeling at the Post, actually sort of election data and modeling at the Post takes a variety of different forms. There are many different data sources that I ended up working with: election results, voter registration data, sometimes polling. But I am mostly sort of focused on the modeling effort. And so for this presentation, I'll actually be talking about 3 modeling efforts that I went through over the last, I suppose, 7 years or so. The first one I'll be talking, so those are voter flow, poll aggregation, and my election night forecasting, which if you all are familiar with, in the German-speaking world, we call that Hochrechnungen. But up until recently, that was sort of not quite as well known in the United States. And so we don't have quite a sort of nice name for it yet. Election night forecasting sounds less fun. So first I'll be talking about voter flows. So which, you know, in the German-speaking world, again, better name, we call them Wählerstromanalysen. So imagine that it's we're in the middle of a presidential primary season and the Iowa caucus just happened. And we have results from the Iowa caucus, and we want to know who Trump's 2024 primary voters supported in 2016. But we don't have any polls, so we don't actually know individual preferences. But we do have the results from 2024, which you can see on the right, and the results from 2016, which you can see on the left. And so sort of squinting at those results, you can actually sort of infer maybe some things. You could see that, Donald Trump is doing very well in 2024 in the areas that he did well in 2020, in 2016, but he's also doing well in areas that Ted Cruz did well in, so the yellow parts on the left. And we can also see that his weakest areas are the ones that Marco Rubio won. So those are the purple ones on the left. And so we can sort of draw, some general inferences from just looking at these maps. To make our life easier, imagine that we just had 4 counties rather than, the 99 counties or so that Iowa actually has. And again, by squinting at these at this table, you can sort of draw some inferences. You can see that, in the counties like Ashua, that Marco Rubio did really well in 2016. That's the sort of leftmost column. That's the place where Nikki Haley did well in 2024. These are not real counties, by the way, and not real results, just sort of to make our life a little easier. So, but we want a systematic way of going about, of understanding what's going on here. And in order to do that, we have this results from 2016 and 2024, but we need to come up with some assumptions. And so there are some basic assumptions that we can make here that will allow us to sort of make more rigorous inferences about the results. And so for 2, very basic assumptions, we can say that every 2016 voter chooses a 2024 option. And then we can also say that the probability of a voter choosing a candidate only depends on their 2016 candidate preference. So that means every person who voted for Ted Cruz in 2016 has the same probability of voting for Donald Trump or Donald Trump or Nikki Haley in 2024. And with those 2 assumptions, we can set up a constrained optimization problem. So the formula for that is at the bottom. And basically, we're saying that Trump's 2024 vote share is a combination of Marco Rubio's vote share times some, constant that is the same for all Marco Rubio voters, plus some percentage of Ted Cruz voters, plus some percentage of Donald Trump's voters. And we know that those fractions need to be between 0 and 1, because basically, between 0 and 100% of Marco Rubio voters in 2016 could have gone to Donald Trump in 2024. And even with such a very basic, setup, we can plug in our table that I showed you earlier, which is in the top left corner here, into R. And on the right, we see like an R function. There's no need to really sort of go into detail here. It's just sort of setting up the problem and trying to solve it. And in the bottom left, you can see the results. And sort of our general intuition from just squinting at the table with, these fake results, so I guess it's not that surprising, is actually correct. So the first number here, which is 0, is our estimate for the percentage of Marco Rubio voters in 2016 that went to Donald Trump, so 0%. And 95% of Cruz voters, and in our very set up problem here, 100% of Donald Trump voters in 2016 went to Donald Trump again in 2024. But the big question we should always be asking ourselves when we are modeling in general, but in particular maybe in a newsroom setting, we have to ask ourselves, do we believe our assumptions? And just sort of a quick reminder what our assumptions were. Our assumptions were that every 2016 voter chooses a 2024 option, and the probability of a voter choosing a candidate only depends on their 2016 candidate preference. And so the first assumption, we don't really believe that, right? Like people leave the state, people die, some people decide not to vote, but there are easy ways we can deal with that, like in constrained optimization, we sort of call that adding a sink and a source. These are just sort of methodological things that we can do to deal with that problem. But the second assumption is actually sort of a little bit more, I don't know, nefarious maybe, more problematic. Like maybe Ted Cruz voters that live in cities are actually quite different from Ted Cruz voters that live in more rural areas. But our model assumes that they're all the same. And so assumptions like that, or violating assumptions like that, if we don't take account for those in our model, can lead to real issues and sort of can lead to bad outcomes and bad outputs, ones that we can't stand behind when we are trying to, talk to our readers about what we found. And so there are ways of refining our approach that can sort of solve this. And I don't want to get too bogged down in details here. Considering that we don't believe our assumptions, we often run multiple methods here in order to try and see whether, they have similar outputs. So we can stratify our regression by covariates. So for example, we could run separate models for, rural counties and urban counties that would sort of separate out the problem that I mentioned before. There are more sophisticated Bayesian ecological models. And, the other benefit is that we can use precincts rather than counties, so more granular data. If we sort of pick one of these, so say stratifying our regression by covariates, If you want to ask me like how good are these models, we actually do have some a bit of validation here. There are occasions when we do also have exit polling. And in times when we do have exit polling, the results of these models actually end up being pretty good. So you can see here that, our exit poll said that 13% of Hillary Clinton voters in 2016 voted for Joe Biden. So this is for the Democratic primary in New Hampshire. And our model prediction said that 12.2%. So you can see pretty close. In general, we've used those models a lot for, writing, publishing stories. We initially built those models for the 2020 Democratic primary, but we really they came to their full force to some degree during the 2024 presidential primary on the Republican side, because that was sort of more competitive in the beginning. And so we wrote a story for Iowa, and we wrote a story for New Hampshire, sort of showing where Donald Trump's support had come from, how he was able to, build on his support from 2016 and really coalesce the right wing of the Republican Party. So that means, in particular, Ted Cruz voters. Ted Cruz had stayed in the 2016 primary for very long, and these voters are the ones that had moved to him versus a lot of the Marco Rubio voters, Kasich voters from 2016 were the ones who, up until the very end of the Republican primary in 2024, kept voting against Donald Trump. All right, that was voter flow. I'll now move on to the task of poll aggregation. So initially, we were, our setting was the Democratic, during primary season. Now imagine time has passed and we're actually in the presidential general election. And, we get many state and national polls. In this case, Trump versus Biden. But we don't get national polls or state level polls every day. So here are a few. Again, these are not real polls from, say, June of presidential years of 2024. There's some national polls here. There's some polls from the state of Georgia, and we want to know who is actually ahead. And we want to know who is ahead both on a national level. So for the popular vote, but also on a state by state basis. And again, we can make sort of assumptions that then naturally let us build a model on top of these assumptions. So I don't want us to get too bogged down in the math here. I mean, similar to before, if you all have questions about the specifics of the math, I'm happy to answer questions later. I want to focus more on the assumptions that we're making. And so the assumptions that we're making is that polls are a glimpse into how voter intentions evolve or are at any given moment. And so polls over time show us how they evolve. And we're going to be modeling voter intentions as a random walk. So what does that mean? That means that the voting intention on day, today, say, is a function of the polls that we're getting today, plus the average that we had yesterday. And another assumption is that our state level estimate is a function of both state and national walk. And this is actually work based on the work of Drew Linzer, who built a full Bayesian model for this. And actually, the math that you can see on the right is from his paper on this. But again, I don't want us to get too bogged down in the math. I think the main takeaway here is that we're again creating these assumptions, and these assumptions in particular are that our polling average on day T or whatever is based on new polls and the polling average the day before. Now again, similarly to the voter flow, I think it makes sense for us to go through the exercise of asking ourselves whether we believe our assumptions. And one good way of thinking about this, so this is actually what happened to us 2 years ago, is that thinking through the exercise, what happens if something big happened that changed the dynamics of the race? So, we all remember that, there was a debate in June of 2024, and Joe Biden did particularly poorly in that debate, and that actually changed the dynamics of the race in a really fundamental way. I sort of highlight here that something happened at that moment, and you can see it being reflected in the polls. First before that, the bottom polls, you can see the polls being really tight, really close. And then sort of after that event happened, suddenly you can see Donald Trump being further ahead in the polls rather than Joe Biden. And so, like I said, our current model just depends on the last days of average and any new information that comes with polls. So the chance that our model would allow for a big movement in the polling average is actually really low. And so, we ran into this issue where our polling average was quite bad at picking up changes that happened really quickly. because of the assumptions that we had made. Our assumption, like I said, was that the polling average cannot change particularly quickly. And things changed very, very quickly from one day to the next. Suddenly polls were looking really bad for Joe Biden. Suddenly, his own party was asking him to step down. And so we had to rely on the fact that, we had been quite intentional about what it was that we had been modeling. Instead of, like I said earlier, we were building a polling average, not a forecast. And so that gave us a bit more leeway in terms of, having this built-in issue in our model. The If we were making projections into the future, we would have been way more reliant on the random walk component of our model, which was obviously, or maybe not obviously, but in retrospect, I can tell you all was a bad assumption for us to be making, or maybe a risky assumption for us to be making, because it sort of narrowed down the scope of what we imagined would be possible. And so the fact that we are not making a forecast, but our model is a snapshot of a current moment, that probably saved us a little bit in our modeling effort. But really, the story here is not, get lucky with what it is that you're trying to model. It's one, being very intentional about what it is that you're trying to model, and B, think hard about the assumptions that you're making initially and how your assumptions might be violated, when you're actually in production, because those can have, the violation of your assumptions can have real world effects, like your model average being too slow to pick up changes that are happening in a presidential election. Again, I briefly want to talk about, how we used our polling average. So we had initially built a polling average page for our output. This is sort of These were some of the takeaways that we had from it. We had sort of the average at this current moment. We had this timeline that you saw here, and then we added some things like what would have happened if a polling error, what would happen if a polling error of similar magnitude to 2016 and 2020 would happen in this presidential election. And this was actually an incredibly popular page. It ended up being the most visited Washington Post page since January 6th of 2021, so basically 3 or 4 years, which was very exciting for us. And we sort of realized that there was a lot of appetite for people being interested in this kind of work. And, especially since we avoided the forecast component, just looking at an average, we were, positively surprised by people wanting this kind of information. We also wrote a number of stories that were really based out of this polling average. And so my job for a few months was basically every day I would run this polling average to, integrate the newest polls. And I would then sort of spend a little bit of time probing around in the polling average with the parameters and, what I was seeing, and coming up with different storylines that we could write about, in order to make this data more useful. And these are 5 stories here. We actually wrote quite a few more. And these all, did quite well. People were really, really excited to see different applications of this data. And so this in many ways was a real testament to being able to use these data science methods in a newsroom and making them accessible to our readers, even if I just showed you all that behind the scenes, we were maybe running into more problems than we had anticipated when we initially set out. All right, so now I'm going to talk about election night forecasting. And like I said, this is what, in the German-speaking world, we would call a Hochrechnung. And so what is the problem that we're trying to solve? In our first model, we were looking at the voter flow model. We were in the primary season. In our polling average model, we were during the presidential election. And now imagine that it's election night of the presidential election. And results are starting to come in. And we want to know what those results mean for the final outcome. And so the screenshot, the unfortunately very low resolution screenshot that I have here, is actually from election night in 2020 from the state of Pennsylvania. It may have been Wednesday after the election. If you all might remember, the election took like 4 or 5 days to be called, and the results were trickling in very slowly. But this was from 2020 in Pennsylvania. And you can see that the red bar, Trump's bar, is ahead of Joe Biden's bar, because that's where we were at with counted votes. But we all know that Joe Biden ended up winning the state of Pennsylvania in 2020. And you can see that the fuzzy bars on the right, which is our projection, The ones for Joe Biden, while the fuzzy parts of the bar still overlap, we can see that the darkest part for Joe Biden is ahead of the darkest part for Donald Trump because our model is, projecting that even though Donald Trump is ahead with the counted votes, Joe Biden will end up ahead when all the votes have been counted based on the distribution of where the votes have been counted. So that's the problem that we're trying to solve. And so to make our life a little bit easier, to get a grip around what it is that we're trying to show, all right, what is it we're trying to do? Imagine that, we're trying to predict the Democratic vote share of the 2021 Virginia election rather than a presidential election. It's a bit easier for us to get our hands around, but the method is exactly the same. And again, to make our life easier, imagine that there are 7 counties in Virginia. And we know these things about the counties. We know the name and we know the county type, suburban, rural, urban. We know the percentage of people in the county that are African American. We know the median household income, and we know the 2017 vote share for the Democrats. And like I said, we're trying to model the 2021 vote share. Now, again, taking a step back, like what is the problem here? Like, why can't we just do this? The problem is that raw results can be misleading. The chart here I have on the right shows what I showed earlier on with the fuzzy bar projection, which is that initially, or maybe very initially, Joe Biden was ahead in the counted votes, but then the raw results were showing that Donald Trump was ahead for most of a couple days or most of the night until Joe Biden took the lead again. And so what's happening here is that early counties are not like late reporting counties. Rural counties generally report earlier than urban counties. Sometimes eastern counties in a state report earlier than western counties in a state. Time zones can have that kind of effect. And so in our scenario here, imagine that we get these 3 results from Fairfax, Hanover, and Greene County. And we just have no idea how representative these results are in any way. And so that's one problem that we have. The second problem that we have is that partial results in counties where we have partial results are not representative for the results as a whole. So in our example, imagine that we get some result, we have full results from Fairfax, but we only have some results from Chesterfield. We have full results from Hanover, 34% for Democrats, but we only have partial results from Mecklenburg. And so we have no idea whether these are, representative in any way for the results of that county as a whole. Imagine that, a place counts their mail ballots before it counts a county counts their mail ballots before it counts their election day ballots. Or maybe it counted their ballots in one part of a county, the more rural part of a county. Some of these counties are very large and quite diverse. And so we just have no idea what's happening under the hood. And so again, reminding us what the problem is, we want to take the partial results from counties that have and from counties that have not finished reporting. And we want to make a prediction about what this means for the final outcome. And so why is this a hard problem? Well, prediction in general, when you're trying to make a prediction, is already very hard, especially in a case like this. We don't have a lot of data. If we're doing this on the presidential level, there are like 300 counties, 3,000 counties across the United States. That's not very much. But, in our toy example here in Virginia, okay, so I gave you 7 counties, but in reality, Virginia has like a bit more than 100 counties, around 150 counties. That's not very much. Imagine that we only see, we want to make a prediction when only a few of those have started reporting, because if we wait too long, then our forecast isn't useful anymore. And so we're trying to make a prediction with not very large data. And the other problem is that our data is not IID, so independent, identically distributed. In particular, imagine that, on a presidential level, we might get data from New York County or LA County. Those are obviously very different from a lot of other counties in the United States. And so they're not in any way identically distributed from most other counties in the United States. In fact, there are very few counties like New York and LA in the US. And so getting results from those counties, for example, might not tell us anything about the results in all other counties. And so the additional reason this is a hard problem is that we also care about uncertainty quantification. We want to be able to build confidence intervals or prediction intervals, or tell our readers how certain we are about the prediction that we're making. And uncertainty quantification is already harder than prediction. But in our case, it's really important because we want to sort of maintain our reputation as the Washington Post, that we are careful about what we're saying and specific and exact about what it is that we're saying. And it's also a data visualization and communication problem. How do we show readers what uncertainty intervals are, what confidence intervals are? They're not at all intuitive. And so that's a problem in and of itself. And so this is why this is, like I said, a really hard problem that we're trying to solve. And so under the hood, what we're doing for our prediction, at least, we're actually using two models. So on the one level, we're using what we're calling the fundamentals model, and then we're using an extrapolation model. And I'll walk through those real quick, one by one. So we'll start with the fundamentals model. So the fundamentals model only focuses on the counties that are 100% reporting so far. I showed you all we have these two sets of counties, those that are 100% reporting and those that are partially reporting. And we actually end up treating those differently from each other. And so we first have this model, the fundamentals model, where we use completed counties and their demographics to understand, what that might mean for the rest of the state. And so in our example, what that means is we take the three counties that I've reported, so Fairfax, Mecklenburg, and Amelia in this case. So it may have been green earlier. May have made a change here. Sorry. We fit a model. So basically just fit a regression using those three counties. And then we predict, and as covariates here, we might use the percentage African American in a county. We may use median household income. And then we project, apply that model, predict, I guess, on the counties that have not finished reporting yet. And even in our really toy example here that we have with these 7 counties, if we do that, we can see what the predictions here are. So for Chesterfield, it's 45% for the Democrats, and the actual result was 47% for Democrats. In Hanover, it was 31%, and the actual percentage was 32% in the end. So even in this really toy example, these are real results, and this is real data, and the model was fit only on these 3 counties. We can see that this model actually does shockingly well, because these demographics, even very basic demographics, are actually really good at making these kinds of predictions for a lot of elections. And so this is, our toy example would have performed very well here. The error, we're really only off by 1 or 2 percentage points for the Democrats in each of those counties. Again, using only 3 counties to fit our model and one covariate, which is a percentage African American. So that's the fundamentals model. So under the hood, it's actually a weighted ridge regression. And, like I said, we're using demographic covariates. But then we actually have this second model, the extrapolation model. And what we're doing here, we want to use the information in non-finished counties also. But like I said earlier, how do we do that, right? We have no idea what part of the county is finished reporting. We have no idea what this might mean for the final outcome. But actually, we are in luck. So reporting effects are actually quite predictable. So what you can see here is Florida's are the error in our prediction on a county level over time. So the prediction being what the current state is at a given moment at say 80% reporting versus what the final outcome was. And we can see that for most counties, the error is actually directionally the same. And the reason for that is that because in a state, usually the counties count the votes in the same pattern, like their early vote first or their election day vote first or something like that. And so we can use that to our advantage. I do want to flag that the reporting effects are only predictable by state. So you can see the same plot here for Michigan, and you can see that the error is actually moving the different direction. So we were over-predicting, we were under-predicting for the vote share for Democrats versus in Florida, we were over-predicting the vote share for Democrats. The specifics here don't matter. The real takeaway is that, nearly all these lines are moving in the same direction. And so we can use that to our advantage. And what that looks like in reality is that we use counties that are further along in the counting process to figure out what the error should be for counties that are not as far along in the election, in the counting process. We build an estimated correction for all the counties in a state, and then we can apply that to all the other counties that are, for not as far along their counting process. And that gives us a second model in order to make a prediction for a given state. And what that actually looks like is in reality is a k-nearest neighbor regression, which we combine these two models, our fundamentals model and our extrapolation model, via ensemble method to get our final prediction. I mentioned earlier that uncertainty quantification is a really important part of what we're doing here. And now that we have our final model, we have to ask ourselves, how do we quantify this uncertainty? And so in a usual setting, if you have a regression, the sort of standard textbook thing to do, if you have a linear model like we do, at least for the fundamentals model, we assume normality, we calculate z-scores, all that kind of stuff. But we can't actually do that because our error distribution is asymmetric and heavy-tailed. It's actually not normal. It's very far from normal. So on the right, you can see a QQ plot here. If our errors were normal, they would all be along that XY line, but you can see they're not. So we would have a lot of problems with assuming normality and z-scores and all those sort of normal approach that you would take based on a textbook. And so what we use instead is we use an approach called the model-free bootstrap. So I don't want to get into too much detail here too. Again, I'm happy to answer questions if you all have them. But generally speaking, the bootstrap is a resampling method that allows us to estimate, uncertainty. We create synthetic data sets. We sort of create many different versions. You can see here we have B versions of our data set where we sample from the counties that have already reported. And that gives us a sense for what the variability in our data looks like, and we can use that to build uncertainty estimates. And so we use this method called the bootstrap. But again, for this presentation, we've been wondering, how do these assumptions work? And the bootstrap actually has many different assumptions. I'm not going to go into detail here about all of them, but here are three important ones. And three of them are that the feature responses, that means the data is random. Again, we have an assumption that the data or the errors are independent and identically distributed. And another assumption is that we have sufficient sample size. And like I said, there are more assumptions that I'm not mentioning. And so again, like in the other two models, I think it's important that we go through the exercise of whether or not we believe our assumptions. And in this case, I highlighted those three assumptions in particular because those assumptions are violated in a really important way in our model. And so we actually have to adapt the bootstrap in quite important ways in order to deal with that. We're trying to minimize the impact of these assumptions in order so that when they get violated, they don't cause our model to do really bad stuff. And so again, I don't want to get into too much detail here. I'm happy to answer questions, but we resample residuals rather than counties. So we fix the features that makes sure that we don't have to assume that our features and responses are random. We stratified the sampling, whether counties, rural, urban, or suburban, that moves the assumption that our data is IID into the assumption that our data is IID within rural, urban, and suburban counties, which is a assumption that is more likely to be true. And then I don't want to get too much detail here, but we build a conformal model, a quantile regression model, conformal quantile regression model, in order to sample the errors. This is sort of helps us with the fact that we often don't have a lot of data early on in the night, and to make sure that our uncertainty that we are capturing is actually larger rather than too small. So we're being, I would say, more conservative here, in order to make sure that our confidence intervals, if they are not accurate, that they're rather too wide rather than too small. Because again, we have this reputation at the Washington Post that we need to make sure we don't accidentally ruin by being overconfident about our prediction. And so putting all this together, what does this mean? We have the model that gets fed on live election results and demographic data and historical election results. We have this fundamental model and the extrapolation model, which are put together as an ensemble that generates the prediction. Those models also get fed to fit a conformal model and the stratified bootstrap, which create our prediction intervals. And our prediction intervals together are what generate our forecast at the bottom. So I just sort of breezed through this quite quickly, and I understand there's sort of a lot of questions, but one question that you all might have is how the hell does one even come up with something like this? And the answer is sort of a lot of trial and error. And so what we built ourselves is we built ourselves a validation package, software basically, that let us rerun past elections from saved results. And that let us tweak our model again and again in different ways in order to make sure that our models would have captured the specific idiosyncrasies of previous elections. It would evaluate the accuracy of our model and whether our prediction intervals would have had the correct coverage. And I want to say, like, I guess I wrote here that we rerun past elections. Our model test bed can actually do more than that. We can generate fake elections that are sort of worst case outcomes. So like what happens if only urban counties report first? If we don't get a single rural county until very late into the night, that's not very likely to happen on election night, but we need to make sure that in these worst case scenarios, our model doesn't do something that's kind of vaguely insane. And so what you all can see here is we built this test bed after the 2020 election. Again, I'm sorry, these charts are a little bit more pixelated than I would have hoped. But the top chart is from Pennsylvania, a rerun of our test bed from 2020. And you can see that, our model very early, or basically from nearly the beginning of the night, predicted that Joe Biden was going to be ahead. It maybe initially overestimated Joe Biden. And then so the prediction sort of settled at around, I think, 1 or 2%, and was very stable. Our confidence intervals, which are the blue thing around the prediction, sort of shrunk over time. You can see this moment in time that I highlighted, the first one here, or I guess the second moment in time that I highlighted here, is when our prediction intervals said that, Joe Biden that Donald Trump had basically no chance, or if less than, whatever, 2% chance, or whatever our prediction intervals were, of taking the lead. And you can see here, basically a couple hours later, the AP, the last thing I noted here, is called the election of Pennsylvania. So we were on a very similar timeline with this model in Pennsylvania, than the AP. And you can see something similar at the bottom with Florida. It sort of flipped. We're showing Donald Trump being ahead. Basically, our model from the get-go assumed that Donald Trump was going to win. It maybe slightly overestimated Donald Trump in the beginning, but again, it settled pretty quickly to a final prediction. And you can see that our model, basically converged on Trump very quickly and very similar time to when the AP called the election. So this is what our model test bed allowed us to do. And this is basically through trial and error how we came up with a model like that. I want to take a brief note about visualization. So I showed you all the fuzzy bars from earlier, and this was our visualization in 2020. We spent a lot of time thinking about how to visualize this model, and this was our first public visualization of our model in the 2020 election. And we've probably focused too much on uncertainty, not enough on prediction. You can see here that we're really highlighting our confidence intervals or prediction intervals. We're not really highlighting our point prediction. And people, including our people internally at the Post, were very confused by these predictions. Our editor-in-chief really didn't like them. She, didn't really understand what was going on. We learned through a lot of trial and error that people ended up focusing on this white space between the prediction, between the fuzzy bars and the actual bar, which was very surprising. I mean, to me, I guess, but that's one of the lessons learned. And so between 2020 and 2024, we moved to this prediction. This was our prediction we used in 2024. So you can see here the counted votes over time, and then you can see our prediction to the 100% counted votes. And you can still see the uncertainty. These are the cones around the prediction, but we're being a lot more specific about what our prediction is. We're actually giving a percentage. We're showing who's actually ahead rather than letting our readers sort of try and infer who's ahead based on the intervals. It was really important to us to be as transparent as possible. Our code for this model is actually entirely open source. You all are welcome to take a look at it. You all are welcome to open pull requests on it. I would be very happy. You can all install the package yourself from PyPy. We've also published different models and different levels of complexity to try and make this as accessible to other data scientists, to other newsrooms, to our readers as possible. I want to make a quick note about assumptions. I want to bring these three models together a little bit. I was really focusing on what the assumptions are on these models. And there really is sort of a spectrum of assumptions that I walked us through here. And, from most assumption heavy, which is probably the voter flow model, to the least assumption heavy, which is the election night forecasting model. And for voter flow, like I said, the assumptions were, the heaviest. And so what we had to do here is we really had to spend a lot of time validating our predictions. So I showed you all that we compared our predictions to exit polls. We spent a lot of time doing that to make sure that, the likelihood that our assumptions would be violated weren't actually that high. For the polling aggregation, the way we sort of tried to get around what our assumptions were doing to the model was that we were thinking really carefully about what it is that we were trying to communicate. And finally, for the election night forecasting model, the way we try and go around these assumptions is that we really tried hard to minimize the assumptions. So, for our predictions, for our confidence intervals, We used the bootstrap, which is, model free. We use conformalization, which again is model free. And so we really try to, be as non-parametric as possible in order, and even within then the bootstrap, we try to use approaches that would minimize assumptions. And again, I mentioned the point earlier that our confidence intervals for the election net forecast were probably a little conservative, so like a little wide. And again, this was one way to sort of get around our assumptions. So if our assumptions are being violated in a way, at least we can fall back on the fact that our confidence intervals are probably a little bit too wide. And so like even in a worst case scenario, or maybe a bad case scenario, the outcome won't be disastrous for our reputation. Finally, I want to talk quickly about some lessons that we learned about modeling in public. The first lesson is that I spent basically 7 years working on this, nearly entirely full time, and this gave me a lot of really deep understanding of what election data looks like. And so the point I want to make here is that subject matter expertise matters a lot when you're doing this kind of modeling. Like when I got these voter flow outputs, I needed to be able to quickly assess whether they looked reasonable. I need to have an understanding of who these pollsters are that I'm putting into these polling models. I needed to know where we can get precinct results from, what states and how, and are precinct results better, and places where they may or may not be better. So that was really important to the work, and I'm not sure I would have been able to build these kinds of models, at least not to the level that I did, without having the ability and the benefit at the post that they gave me to really focus hard on this kind of work. Another thing that I learned is that interpretability really matters. So these are actual Slack messages that I got on election night from our editors. They wanted us to be able to say things about our model, publicly, like what was actually happening under the hood. Why was the model showing the things that it was showing? And that was only possible because our model was incredibly interpretable. So like I said, the fundamentals model was basically just a linear regression. And so you can take a look at the parameters and you can actually say things about those, what the model is actually doing, make claims. And so, it was really important for us that we're able to do that with these models. So rather than using really sophisticated neural networks or whatever sophisticated models that could have squeezed out maybe an additional, tenth of a percentage point in accuracy, we rather went with models that are more interpretable because, it let us be more communicative with our newsroom and also with our with our readers about what it is that we were seeing. Another lesson is that it's good and important to focus on uncertainty, but not to the point of obfuscation. So like we wanted to make sure that our readers understood that our predictions came with a band of confidence about how likely it is that, we are saying what we're saying. But we probably erred in our initial model, in our initial visualization, too much on the side of uncertainty. We were like obfuscating the thing that people actually cared about, which is in the end, they care about who's going to win, right? Like, yes, of course, they want to know like how likely is it that the person's going to win, but they really just kind of want to know who's going to win. And so, focusing on uncertainty is good and is important because it's honest, but it's important to remember what it is that people are trying to get out of your modeling effort and give them the thing that they actually want. Be clear about your assumptions. I mean, this I think is something that I tried to, make very clear during this presentation. This is something that we spent a lot of time thinking about during these modeling efforts. Writing down the assumptions that were going into our model and thinking through one by one what happens if these assumptions get violated in different ways and how bad is that for the model. How do voters change their minds in Biden primaries? Would a random walk capture Biden's debate performance? The answer is no. Is it important to do more than just stratifying by rural, urban, suburban classes in the election night model? So really just, being clear about what it is that is flowing into the model so that you get a better understanding of what happens when things go badly. And then finally, that transparency is key to trust. We try to be as open and public about our work as possible. I've talked about our work publicly. I've written about our work publicly. We try to make as much of our code open source as possible and available to the public to see. Obviously, we are aware that a general reader of the Washington Post is not going to go onto GitHub and look at our code, but other data scientists might, and other data journalists might, and have in fact. And that gives us credibility with those other news organizations and those other data scientists. And we're hoping that generates sort of that percolates our, the trust that we're generating with these people across different organizations and hopefully down to our readers at the end. Yeah, those are the lessons that I spent the last 7 years putting together, I guess. Thank you very much.
Thank you. Thank you so much, Lane. That was a lot to chew on, and I guess people will have questions. I'm happy to take questions online and on site. If you're online, just raise your virtual hand, and then I'll put you on the list. And we'll figure out how that works with your questions here, whether the audio is sufficient. Otherwise, I would just like ask you to come forward and then ask the question. So, are there any questions? You want to maybe just speak up a little, and then
It's really cool.
Lenny can tell us whether you can hear it more.
Yeah, sure, it's really cool.
I think it's better when you can. Yeah.
Where do I still?
Let's use my camera. I'll just unblur it.
So, hi Lenny, thank you for the talk. I was really interested in the vote flow model, especially specifically if you know any limits on the application of it in other countries or electoral contexts, whether it's applicable or not, because since of the particularities of the US district system. And also, if you think you could maybe apply it for election forecasting in the sense of like, yeah, having this data, can you predict the next US electoral cycle? Or is it like
Yeah.
because you have different candidates, it's a different story? Yeah, just talk about it.
Yeah, that's two great questions. The first one is that, the voter flow, it's actually not a great fit for the US elections because there are only two parties and there's not actually that many voters that flow back and forth, but it is a good fit for the primaries. And so, we learned this from basically a lot of countries that have multi-party systems use these voter flow models. Because it's sort of more clear when there are many parties and people move between the parties. And so it's actually a really good application or a really good fit for, multi-party countries. I will also say that a lot of countries that have these kinds of models sort of baked into their election night reporting process. So this is true in Germany, for example, and Austria. They actually ask these questions in exit polls also. And so it's not just the modeling. They have then two approaches to this. They're using the modeling, like similar to what I do, and they also have polls, and they want to make sure that those things match. So they basically have both of those things go in. We just didn't really have the polling for the most part, and so we had to rely on the modeling. And then the other thing is whether we can use it for predictions. So yes and no. I think it would be really hard to use it for predictions for the future election. But where it did help us a lot was it gave us a prediction for future primaries. So we could apply the like Iowa voter flow and make a prediction for the next primary in New Hampshire. And we actually saw that those models ended up being really good in the context of the 2024 presidential primary. That's because the like battle lines, so to say, were very hardened, right? There was like the Trump team and there was the anti-Trump team, and Republicans would fall into one of those two camps during the primaries. And so Nikki Haley's result in one primary was actually very predictive for her result in the next primary because she was able to basically get the people who had voted for Marco Rubio and John Kasich or whatever over and over again. And so applying those models, fitting the model in one state and applying them to the next state, we were able to generate predictions for other primaries in the future, and they were actually very predictive. But I would be more weary about applying them into elections that are not with the same candidates, basically.
Take Linus online. Linus, do you want to just unmute? Yes.
Yeah, perfect. First of all, thank you so much. That was extremely interesting. I have a question that is only partially related to forecasting, but more to like polling in the US context. Because what I really liked about the models you presented is that they are like quite close to actual data, right? Like there's not much secret sauce going into that. And there was this discussion about, I don't know, I think one of the latter ones was the Hispanic vote that like moved from the Democrats to Trump and maybe now back, and people relied on that and then they got bitten bad. And my impression was that like relying on these, let's say, yeah, I might just call them feelings, has gotten a bit out, isn't on vogue as much anymore, but I would be interested if you have an opinion on that, on how you look at these things, and maybe if your stance shifted over the last, I don't know, 4 or 5 years.
Yeah. So I guess I try to keep a little bit more of a holistic approach to the outputs here. So, like our models that I presented can give you an estimate of for demographics, like how many, the model estimate of the percentage of Hispanics that voted for Donald Trump is something that we can get out of our model parameters. And sometimes it agrees with the exit polls, and sometimes it doesn't agree with the exit polls or polls in general. And my approach has always been like, it's very good if they agree, then we can feel more certain. If they disagree, then like try and I'm not saying that the polling results are bad. I'm also not saying that the model results are bad, but it opens an interesting discussion for why they disagree, because that means that the individual level results are different from the aggregate level results. And so like there might be good reason for that being true. In fact, there are many examples of, making inferences based on, election results only about demographics are actually misleading, right? There's a whole field of ecological inference and ecological fallacy and all that exists and is true. But sometimes polls are bad. I mean, like we have seen that happen again and again recently. And polls sort of don't capture a specific audience or underestimate a specific candidate. And so the subgroup polls they're high variance and they also have those problems. And so my approach has basically been like, if the ecological results and the polls agree, very good. If they don't agree, there's a bigger question to be asked here. And it's not obvious to me from the get-go which of those two we should rely on. Did that answer your question? Cool.
I'll put myself on the list. Lenny, you talked about uncertainty visualization and like how to communicate uncertainty more generally. And if I got you right, you have a pretty pragmatic take saying yes, we should make clear that like there's always uncertainty involved, but also we shouldn't overdo it. And that had an influence also on how you visualized, say, like genuinely uncertain components of the output. My question is, when you incorporate feedback on that, is that an iterative process, or is this systematic? Do you even do experimentation on that, or does basically intuition plus feedback trump, say, like the classic, say, scientific setup where we would have the bulk of ways to, say, like visualize uncertainty and then see what works best? What's the approach there?
Yeah, so I'll actually say that I've changed my view on this over time. So I used to be, I mean, as you can see with the initial visualization, I was very like uncertainty forward. I was like, we try to be very clear about the uncertainty because we don't want to mislead our readers about how specific it is that we're trying to say. And that's really dangerous if we do that. And, maybe part of it was also kind of a sort of cover my ass sort of thing. Like I was scared that if I was wrong publicly, I could I could sort of hide behind the uncertainty quantification in a way. And it was an iterative process. I mean, like we did experimentation with our readers. We had focus groups. We had focus groups in-house at the Post, like our editors and stuff who are not as quantitative. And also our readers, basically, we polled or like had focus groups for our readers. The initial visualization that we had was very obvious to me, right? Like I would looked at this and I was like, I understand exactly what this is. And I learned that that is actually not true for a lot of our audience. And, maybe to some degree that was a hard pill for me to swallow, but it was an important, lesson. And to get to this, we still put down a list of things that was important for us. We wanted to make sure that we were only showing one prediction at any given moment. We didn't want to show our prediction over time, because our prediction is our best guess right at this moment, and it doesn't make sense to show our readers our prediction over time. And so we still had like specific ground rules that we were going with, but we had to experiment with what it is that we're showing and, be clearer about the actual thing, because in the end, like I said, people want to know who's winning. And so, you have to meet the people where they're at.
Makes sense. Questions in the room? Just feel free to let me know. I have a couple of more questions on my list, so just continue following Lenny here. then I'll do a follow-up. So I'm like related to that is, and you touched on that, is a reputation game, right? So that there is something to lose in the context of like communication around elections and forecasting. Um, there's something to win. In my experience, like the polling average thing, that is sort of like low risk, right? Like everybody's doing it. There is not so much variation. But say when you add fundamentals and like your own secret sauce, A, it becomes more difficult to communicate, and B, it might give you a result that is completely unintuitive or maybe difficult to explain. Say at the editorial level, how would you say deal with that? Like, would you like try and convince, say, like the non-technical, but like the decision people basically in your team that like modeling makes sense, or how can I imagine that kind of discussion?
Yeah, I mean, it was always a big backwards and forwards sort of thing. Like that we had editors that were more suspicious of this kind of work and editors that were less suspicious. We spent a lot of time convincing them, especially the election night model. I mean, to your point, that's way riskier than a polling average. When I will say I pitched the polling average years into having already done an election night model, so they were very happy to accept the polling average. Also, this came in the context of 538 shutting down, and so they were aware that there was space for this kind of stuff, and they wanted for us to get into the space more. And yeah, it was less dangerous. Had I pitched a full forecast, right, like what does this mean for that final outcome, that maybe would have had more pushback from our newsroom side. But the election night model was a real back and forth. I mean, it helped that the New York Times has the needle, and if the New York Times has something, then the Washington Post needs it too. And so that was always that was helpful for us in some ways to fight this battle. But it needed a lot of handholding and a lot of convincing and a lot of testing this behind the scenes to show our editors that nothing bad happens. Um, and it was yeah, it was a real process. And every once in a while, like our top editors would change, and then we had to start this whole process from the beginning, and that sometimes became a little bit frustrating.
I have one more question, but again, if anybody wants to come in with another one, I prioritize that. There are a lot of students in the room who will do data science, have applicable level skills, but data journalism or like working in this context is an option. Now, a parallel development that we're seeing is like the rise of AI and the use of those tools to like not only change modeling workflows, but also say have your writing heavily influenced or even be entirely driven by that. Now you have given us examples where I think the value of like down to earth modeling became obvious, and like the transparency point I think came through, and explainability point they came through. What is your take on that? Like having the newsroom experience, is there like what skills should people focus on, pick up to well be prepared for a job market better?
Yeah, I mean the advice that I usually give, and I actually maybe should think about this a bit harder now in the time of AI, whether this still entirely applies the exact same way that I always gave this, is the point that I made here, which is that like pick data that you really love and are interested in and become like an expert in that. Because our the LLMs that we have, at least at the moment, they average information, right? But knowing the average of some information is actually not at all that useful when you are building these kinds of models. You need to understand the like weird outlier, the like what happens if a completely non-average event happens, right? Like the election night model works perfectly well for an average election night. And then might come an election where something really weird happens, and we need to be prepared for that. And you can only imagine those scenarios if you have a lot of experience, because you may have seen one election where something similar happened. And these larger language models, they're not going to give you that kind of output because they are trained on averaging information. I mean, that's exactly what they do. And so I don't think the subject matter expertise component is going to go away anytime soon. Like really deep understanding of data, what bad data looks like, what to do in a situation where you get bad data. And so that has always been my advice, and I think I stick to it, is that, like I said, pick a data set or a subject that you are very passionate about and really try and understand what it is that's going on under the hood here. Where does the data come from? What does it look like when it's bad? What does it look like when it's good? What can go wrong in the data generation process? What can you do to fix the data generation process? Or can you not do anything? Are there then modeling approaches that you can take downstream if you can't fix the data generation process? Things like that. I would say that has been my strongest advice here. I think we are all seeing that, like, becoming an excellent software developer, that might be a skill that is maybe going away a little bit. And most of these models were built, the code was written in a mostly completely pre-generative AI time. That's not true for our election AI model. And we used our generative AI in some things, right? Like at the time, it was not as good at a lot of things. We used it for like database reading, and we're writing a lot of boilerplate code. Obviously, they can do a lot more than that now. And I think it's good to use them. Like, actually, it's really good to use them because they, save a lot of time. But you can only find the issues in your LLM generated code if you understand the subject matter really well. And so that's another place where it is actually really important to be a subject matter expert. So that, like I said, is my general overarching advice for students who are looking for work in data fields more broadly.
Thank you, Lenny. I take this as positive news, actually, for all of you. So become experts. You're becoming experts in something already. So I think that's great. All right. We've gone over time a little bit already. Thanks so much again, Lenny, for joining us from the East Coast, for staying up early for this talk. It was great to have you. And thank you, everybody, for joining the series. We're going to reconvene in 2 weeks from now with a talk by Liu Yang from Complexity Hub from the University of Vienna. So there's some like Austrian dominance in the series, I suspect. So be sure to tune in again. And yeah, thanks again for joining.
Thank you so much for having me.